Good day, everyone. So for this week, we will be discussing rank of a matrix and systems of linear equations. For this week's course outcomes, we're going to find the basis of the row space, basis of a column space, and rank of a matrix. We would also be finding the null space of a matrix, find the solutions. We will also find the solution of a consistent system AX is equal to B in the form XP is plus XH. Row space, column space, and rank of a matrix. In this section, you will investigate the vector space spanned by the row vectors or column vectors of a matrix. For an m by n matrix A, we know that there are n tuples corresponding to the rows of A are the row vectors of A. So if this is your matrix A, one of the possibilities that the vectors are written as rows or row spaces. So this is the first vector, the second vector, and so on. So this matrix A is spanned by row vectors. So this set of vectors are augmented together. Similarly, if we have m by 1 matrices corresponding to the columns of A are the columns of vectors A. So this time, your vectors are written vertically as columns of the matrix. So the first vector would be this vector, the second one, and the last one. For example, if we have the matrix 0, 1, 1, and the row vectors are 0, 1, negative 1, so these are the row vectors, 0, 1, negative 1, and negative 2, 3, 4. So row 1 and row 2. So these two vectors form a basis for the row space R cubed. Now, for the column vectors, so we have three vectors. So the column vectors are 0, negative 2, 1, 3, and negative 1, 4. Definition of row space and column space of a matrix. Let A be an m by n matrix. So we have the matrix with m by n. The row space of A is the subspace of R raised to n spanned by the row vectors of A. So the row space of A is the subspace of R raised to n spanned by the row vectors of A. So your vectors would be row 1, row 2, row 3, and so on. So we're going to select the vectors that form a basis. And that set of vectors form the row space. Now for the column space of A, this is the subspace of R raised to m spanned by the column vectors of A. So if this is your matrix, so the space spanned by the given set of vectors form a basis for R raised to m. Now if an m by n matrix A is row equivalent to an m by n matrix B, then the row space of A is equal to the row space of B. So if two matrices are row equivalent, they have the same row space. So if this matrix A is row equivalent to another matrix B, so this is A, this is B, their row space are equal. If a matrix A is row equivalent to a matrix B in row echelon form, then the non-zero row vectors of B form a basis for the row space of A. So we are going to find the row equivalent, and the row equivalent, the non-zero rows of the row equivalent form a basis for the row space of A. As an example, let us consider this matrix A. So for this matrix A, we have 1, 3, 1, 3, 1, 3, 0, 1, 1, 0, negative 3, 0, 6, negative 1, 3, 4, negative 2, 1, and 2, 0, negative 4, 2. The solution to this matrix, the solution to the row space spanned by this matrix will be obtained by taking the row echelon form. So we're going to convert this into its row echelon form. We will be providing the solution to this matrix, the transformation of this matrix in the row echelon form in the file section of our course. Now, the row echelon form of that matrix would be vector 1, the subspace 1, which is 1, 3, 1, 3. The second element, 0, 1, 1, 0. And the last vector, 0, 0, 0, 1. So these three vectors in the row echelon form of the given matrix form the basis for the subspace. Thus, this is the row space. So the row space of A is 1, 3, 1, 3, 0, 1, 1, 0, and 0, 0, 0, 1. So this form a basis for the row space of A. So we are going to disregard the 0 rows. So the non-zero rows form the row space of A. Find the basis for the column space of matrix A from example 2 by finding a basis for the row space of A transpose. So meaning, what we are going to do is to transpose A because the vectors are written horizontally. So what we want to do, so if this is your vector 1, you want to write it vertically as a column space. So we transpose the row space to get the column space. So the component of the vector is written vertically. For row space, the components are written horizontally. For column space, the elements are written vertically. So for this one, so we, instead of 1, 3, 1, 3, 0, 1, 1, 0, so we're going to write it down vertically. So 1, 3, 1, 3, 0, 1, 1, 0, and so on. Now again, we perform row echelon form, and this is the resulting matrix. Now from the resulting matrix, we're going to identify the non-zero rows. So the non-zero rows would then identify the elements that form a basis. So that would be the first, the second, and the third rows. Specifically, the first column, the second column, and the third column form a basis. So therefore, the vectors that form a basis would be 1, 0, negative 3, 3, 2, 0, 1, 9, 5, 0, 1, 9, negative 5, negative 6, and 0, 0, 1, negative 1, negative 1. So 1, 0, negative 3, 3, 2, 0, 1, 9, negative 5, negative 6, and 0, 0, 1, negative 1, negative 1. So that forms a basis for the row space of A transpose. This is equivalent to saying that the column vectors 1, 0, negative 3, 3, 2, 0, 1, 9, negative 5, negative 6, and 0, 0, 1, negative 1, negative 1, all of the transposes of these vectors form a basis for the column space of A. So that would be 1, 0, negative 3, 3, 2, 0, 1, 9, negative 5, negative 6, and the third vector is 0, 0, 1, negative 1, negative 1. These three vectors form the basis for the column space.